Welcome students to the fourth lecture on infinite series. In the previous class, we have seen the Taylor series expansion for a function f x as f a plus f prime a into x minus a upon factorial 1 plus f double prime a into x minus a whole square upon factorial 2, like that, the kth term being x minus a whole to the power k upon factorial k. So, this infinite series, which is a polynomial in x, is an approximation of the function value at x when the function is infinitely differentiable at the point a. If we take instead of the infinite series up to some nth power, then we get a polynomial approximation of f x, but there will be an error term and that error term goes to 0 as k goes to infinity. That is, the higher will be the degree of polynomial, the closer will be the approximation of f x. In the last class, we have also seen the Taylor series expansion for sin x, cos x, tan x. These trigonometric functions we have approximated using their corresponding Taylor series by expanding them up to some finitely many terms. In today's class, let us start with an inverse trigonometric function, that is tan inverse x. So, find the Taylor series approximation of tan inverse x up to x to the power 5. We can do it even beyond that, but this will give us the idea how to work out this problem. So, f x is equal to tan inverse x therefore, f 0 is equal to 0. It is clear that we have taken a to be 0, that is, we are expanding the series about 0. F prime x is equal to 1 upon 1 plus x square is equal to 1 plus x square to the power minus 1. Therefore, f prime at 0 is equal to 1. Let us calculate the second derivative. Let me write it f 2 x, which is d dx of 1 plus x square to the power minus 1 is equal to minus 1 plus x square to the power minus 2 into 2 x is equal to minus 2 x into 1 plus x square to the power minus 2. Therefore, if double prime x is equal to 0 at x is equal to 0. The third derivative of f is equal to d dx of minus 2 x into 1 plus x square whole to the power minus 2 is equal to minus 2 into 1 plus x square whole to the power minus 2 plus minus 2 x into minus 2 into 1 plus x square whole to the power minus 3 into 2 x is equal to minus 2 into 1 plus x square whole to the power minus 2 plus minus 2 into minus 2 is equal to plus 4 x into 2 x is equal to 8 x square into 1 plus x square whole to the power minus 3. Therefore, the third derivative at 0 is equal to, we see that this term becomes 0 when we put the value of x is equal to 0, but here by putting x is equal to 0 we get minus 2. Therefore, the fourth derivative at x is equal to d dx of minus 2 into 1 plus x square whole to the power minus 2 plus 8 x square into 1 plus x square whole to the power minus 3 is equal to 4 into 1 plus x square whole to the power minus 3 multiplied by 2 x. That is from the first term. From the second term we get, actually it is a product of two terms. So, we will get 16 x into 1 plus x square whole to the power minus 3 plus 8 x square into 1 plus x square whole to the power minus 4 into 2 x, which is equal to 8 x into 1 plus x square whole to the power minus 3 plus 16 x into 1 plus x square whole to the power minus 3 plus 8 x cube into 1 plus x square whole to the power minus 4. This is equal to 24 x into 1 plus x square whole to the power minus 3 plus 8 x cube into 1 plus x square whole to the power minus 4. Therefore, f 4 at 0 is equal to, putting the value of x is equal to 0, here we get this is 0, here also it is 0, therefore, the whole term becomes 0. In order to get the approximation of polynomial of degree 5, we have to differentiate it once more. Therefore, f 5 x is equal to d dx of 24x into 1 plus x square whole to the power minus 3 plus 8x cube into 1 plus x square whole to the power minus 4, and this is going to be 24 into 1 plus x square whole to the power minus 3 plus 24x into 1 plus x square whole to the power minus 4 into 2x plus other terms, and you can see that since it is x cube, its derivative will also have an x, and since it is 1 plus x square, its derivative will also have an x. Therefore, the derivative of the product will always contain an x in both the terms, and therefore, by putting 0, this will definitely give us 0. So, therefore, the only non-zero term that this can produce is equal to 24 into 1 plus x square to the power minus 3. This will also give us 0. Therefore, f 5 at 0 is equal to 24. Since we said that we will expand it up to a 5th degree polynomial. So, if we recollect, we can see that f 0 was 0, f prime 0 was 1, f 2 at 0 was 0, f 3 at 0 was minus 2, f 4 at 0 was 0, and f 5 at 0 was 24. Therefore, the 5th degree polynomial approximation for tan inverse x is, now you can easily understand, it is going to be x minus 2x cube upon factorial 3 plus 24 x to the power 5 upon factorial 5, which on simplification becomes x minus x cube by 3 plus x 5 by 5. So, that is the approximation of tan inverse x when we go up to the 5th degree polynomial. Now, you can do it in a slightly more tricky way. If you notice that d dx of tan inverse x is equal to 1 upon 1 plus x square. The expansion of 1 upon 1 plus x square, which is nothing but 1 plus x square whole to the power minus 1, and this is going to be 1 minus x square plus x to the power 4 minus x to the power 6, like that. This we know from the expansion of 1 plus x whole to the power minus 1, and that is going to be 1 minus x plus x square minus x cube. Replacing x by x square, we get this series. Now, let us integrate both sides. Therefore, 1 upon 1 plus x square dx is equal to, by integrating this term by term, we get integration of 1 dx minus integration of x square dx plus integration of x 4 dx, etc., plus a constant c. Now, the left hand side will give us tan inverse x, and right hand side will give us x minus x cube by 3 plus x 5 by 5 plus c, where c is the constant. By putting x is equal to 0, we find that c is equal to 0. Therefore, the desired expansion of tan inverse x is x minus x cube by 3 plus x to the power 5 upon 5. Once we have done with tan inverse x, it gives us the impetus to do similar thing with respect to other trigonometric functions. For instance, consider sine inverse x. What is going to be its Taylor series expansion? We know that d dx of sine inverse x is 1 upon root over 1 minus x square. This is equal to 1 minus x square whole to the power minus half. And we know the expansion of 1 minus x whole to the power minus half, and from there we should be able to get the time series expansion of sine inverse x. We proceed in the following way. Let us first expand 1 minus x square whole to the power minus half. This is equal to 1 plus minus half into minus x square plus minus half into minus half minus 1 upon factorial 2 into minus x square whole square plus minus half minus 1 into minus half minus 2 upon factorial 3 into minus x square whole cube. This is equal to 1 plus x square by 2 plus 1 into 3 upon 8 x to the power 4 plus 1 into 3 into 5 upon 8 into factorial 3 x to the power 6, etc., which is equal to 1 plus x square by 2 plus 3 by 8 x to the power 4 plus 15 upon 48 x to the power 6 . Therefore, now we integrate both the sides. Therefore, integration of root over 1 minus x square dx, by integrating term by term we get x square by 2 dx plus 3 by 8 x to the power 4 dx plus 15 upon 48 x to the power 6 dx etc. plus a constant c, or sin inverse x is equal to x plus x cube upon factorial 3 plus 3 x to the power 5 upon 40 plus 15 upon 48 by 7 x to the power 7 plus c. Putting x is equal to 0, we get c is equal to 0. Therefore, the Taylor series expansion for sin inverse x is x plus x cube by factorial 3 plus 3 x to the power 5 upon 40 plus 5 to 16 into 7 x to the power 7. This we get when I am expanding it up to the 7th power of x. The obvious question is, therefore, what is going to be the expansion for cos inverse x? So, we can find it from the first principle by computing f prime, f double prime, f triple prime, etc. We can find it out from the expansion of sin inverse x, because we know that sin inverse x is equal to pi by 2 minus cos inverse x, or cos inverse x is equal to pi by 2 minus sin inverse x. Therefore, by inserting the value of sin inverse x, we can get that cos inverse x is equal to pi by 2 minus x minus x cube upon factorial 3 minus 3 x to the power 5 upon 40 minus 5 into 16 into 7 x to the power 7, like that. So, from one result we can easily derive some other results if we know their mutual relationship. Let us now look at some other function. For instance, let us consider log of 1 plus x. So, let us start with this. F x is equal to log of 1 plus x. Therefore, f 0 is equal to log of 1 is equal to 0. F prime x is equal to 1 upon 1 plus x. Therefore, f prime 0 is equal to 1. F double prime x is equal to derivative of this, which is equal to minus 1 plus x whole to the power minus 2. Therefore, f double prime at 0 is equal to minus 1. F triple prime x is equal to derivative of minus 1 plus x whole to the power minus 2, which is going to be 2 into 1 plus x to the power minus 3. Therefore, f triple prime at 0 is equal to 2. The fourth derivative of x is going to be minus 6 into 1 plus x whole to the power minus 4. Therefore, f 4 at 0 is equal to minus 6. Therefore, we can see that log of 1 plus x can be expanded as x minus x square by 2 plus 2 x cube upon factorial 3 minus 6 x to the power 4 upon factorial 4 is equal to x minus x square by 2 plus x cube by 3 minus x to the power 4 upon 4, like that. So, it is alternatively minus and plus, and the summation is, therefore, the series is sigma x to the power k upon k into minus 1 to the power k minus 1, which will ensure that every alternate term is equal to minus and plus, k is equal to 1 to infinity. So, this is the expansion of log of 1 plus x. But if we, since we know expansion of 1 upon 1 plus x, we can attempt the problem in a different way. 1 upon 1 plus x is equal to 1 plus x whole to the power minus 1 is equal to 1 minus x plus x square minus x cube plus x to the power 4, like that. Therefore, by integrating both sides, minus x dx plus x square dx minus x cube dx plus x to the power 4 dx plus c. Therefore, log of 1 plus x is equal to x minus x square by 2 plus x cube by 3 minus x to the power 4 by 4 plus x to the power 5 by 5, etc. So, we can see that we can get the same answer even in this way also. Only thing left is to determine the value of C at x is equal to 0, log of 1 plus x is equal to log of 1 is equal to 0. Therefore, C is equal to 0. Therefore, we get the above series as the expansion of log of 1 plus x. Now, by putting x is equal to minus x, we get log of 1 minus x is equal to minus x square by 2 minus x cube by 3 minus x to the power 4 by 4, etc. That is, all the terms here comes out to be negative sign. Once we have the expansion for log 1 plus x, let us consider the next problem. What is the expansion of log of cos x? Log of cos x for x belonging to minus pi by 2 to pi by 2. We know that in this range cos x is going to be positive, therefore, log is valid. Let me do it from the first principle. F of x is equal to log of cos x. Therefore, f at 0 is equal to log 1 is equal to 0. F prime x is equal to 1 upon cos x into minus sin x is equal to minus tan x. Therefore, f prime at 0 is equal to 0. F double prime x is d dx of minus tan x is equal to minus 1 plus tan square x. Therefore, f 2 at 0 is equal to minus 1. The third derivative is equal to minus 2 tan x into 1 plus tan square x is equal to minus 2 tan x minus 2 tan cube x. Therefore, if third derivative at 0 is equal to 0, because if we put x is equal to 0, then this becomes 0 and this becomes 0 as well. Therefore, the fourth derivative of x is equal to minus 2 into 1 plus tan square x minus 6 tan square x into 1 plus tan square x is equal to minus 2 minus 2 tan square x minus 6 tan square x minus 6 10 to the power 4x is equal to minus 2 minus 8 tan square x minus 6 tan 4x. Therefore, f4 at 0 is equal to minus 2. In a similar way, f5 at x is equal to minus 16. I am differentiating this with respect to x. So, minus 16 tan x into 1 plus tan square x minus 24 tan cube x into 1 plus tan square x is equal to minus 16 tan x minus 16 tan cube x minus 24 tan cube x minus 24 10 to the power 5 x, or f 5 x is equal to minus 16 tan x minus 40 tan cube x minus 24 tan 5 x. Therefore, f 5 at 0 is equal to 0, as all these become 0 at x is equal to 0. Let me go one more step. So, what is going to be f 6 of x? This is going to be minus 16 into 1 plus tan square x plus other terms, which by now we know that all of them will become 0 when we put x is equal to 0. Therefore, f 6 at 0 is going to be minus 16. Therefore, we find that for log of cos x, f at 0 is equal to 0, f prime at 0 is equal to 0, f second derivative at 0 is equal to minus 1, third derivative at 0 is equal to 0, the fourth derivative at 0 is equal to minus 2, f 5 at 0 is equal to 0, and sixth derivative at 0 is equal to minus 16. Therefore, the series expansion is minus x square upon 2 minus 2 into x to the power 4 upon factorial 4 minus 16 into x to the power 6 upon factorial 6, etc., which is nothing but minus x square by 2 minus factorial 4 is equal to 24. So, it is x to the power 4 upon 12 minus x to the power 6 upon it is 16 upon factorial 6, which is 720. So, x to the power 6 upon 45, etc. So, that is the series expansion for log of cos x. You can also do it in a different way. We can write log of cos x is equal to log of 1 plus cos x minus 1. This term in minus pi by 2 to pi by 2 will always remain between 0 and 1, and therefore, this expansion is valid, and we have already found the expansion of log of 1 plus x for mod x less than 1, and therefore, this can be expanded by considering this as the term and expanding it using the expansion of log. I leave it as an exercise for you to practice. Now, let us come to one of the most important concepts of mathematics, that is Euler's constant. E. All of you have been using E because the natural logarithm that we take is against E, and E is defined as limit n goes to infinity 1 plus 1 by n whole to the power n. You may wonder where from this term has come. So, let me give you a brief idea. Suppose there is a time period t in which the money that you deposit here at this time point gets doubled at this time point. Therefore, if you put x amount of money here, at this point the money becomes x into 1 plus 1, that is, it gets doubled. So, this is the interest rate over this time period. Now, this money will not remain the same if we pay the interest at an intermediate time. Suppose we decide to give some interest at this point and reinvest the total amount, and then we calculate what is going to be the total amount of money at this point. So, if the total amount of interest till this point is 1, in the half of the period the interest rate is going to be half. So, x amount of money at this point is going to be x into 1 plus half, and this amount of money reinvested here. So, at the end of this time period it is going to be x into 1 plus half whole square. This you must have seen in calculation of compound interest. Now, let us increase the time period further. Suppose we decide to give 1/3 interest at this point, 1/3 interest here and 1/3 here. Therefore, by the same logic x amount of money at this point is going to be x into 1 plus 1 upon 3, which at this point is going to be x into 1 plus 1 upon 3 whole square, which at this point is going to be x into 1 plus 1 upon 3 whole cube. Thus, you can understand that as I am making more partitions and paying the interest at each of this time point, then the amount that we receive is different. So, what is going to be the amount if I partition it at in time periods? By the same logic, we can see that this money is going to be x into 1 plus 1 upon n whole to the power n. So, that gives you an idea where from these terms come, 1 plus 1 upon n whole to the power n. So, as n increases with time, shall we get infinite amount of money? That will depend upon where does it converge. So, I wanted to calculate for your benefit the value of this at some n points. For example, at n is equal to 2, it is 1 plus 0.5 whole square, which is equal to 2.25. At n is equal to 10, this is 1 plus 0.1 whole to the power 10, which is going to be roughly 2.594. At n is equal to 100, we get 1 plus 0.01 whole to the power 100, which is going to be 2.7048. If you have access to some scientific calculator, you can compute these and go up to 4th decimal place. You will find that the values are coming out to be like this. At n is equal to 1000, it is 1 plus 0.001 whole to the power 1000, which is going to be 2.7169. At n is equal to 10,000, it is 1 plus 0.0001 whole to the power 10,000, which is equal to 2.7181, and at n is equal to 1 lakh, it is 1 plus 0.00001 to the power 1 lakh, which is going to be 2.7183. So, we can see that the values are increasing, but not at a very high rate. In fact, as n goes to infinity, 1 plus 1 upon n whole to the power n will converge to a constant, which is 2.71282828459045. There is no end, as this is an irrational number. We will never come to an end of this sequence, and people have tried to compute up to 1000 decimal places, there was no convergence. So, this irrational number is called Euler's number, and which is denoted by E. So, let us consider 1 plus 1 by n whole to the power n. What is going to be the kth term? We can see that it is a binomial expansion. So, for a given k, if we consider n greater than k, then the coefficient is going to be n into n minus 1 into n minus k minus 1 upon it is n c k. So, it is factorial k, or in other words into 1 by n whole to the power k. So, this is going to be the kth term. We get it from n c k into 1 by n whole to the power k. Now, if we cancel out this n, we get it as 1 into 1 minus 1 by n into 1 minus 2 by n 1 minus k minus 1 by n upon factorial k. Therefore, as n goes to infinity, the kth term is 1 upon factorial k. Therefore, the series 1 plus 1 by n whole to the power n goes to 1 plus 1 plus 1 upon factorial 2 plus 1 upon factorial 3 plus 1 upon factorial k In the next class, I shall solve some problems involving the Euler constant and its expansion. Thank you so much.